All right, so let's do a couple examples with linear independence. So we're just going to ask if a couple of sets are linear independent. Okay, so first set we're going to ask, let me get my page out. I had this planned out. So are the functions x squared minus 1, and 5 on negative infinity to infinity linearly dependent or linearly independent? Okay, and these maybe you can sort of guess, but these are going to be linearly dependent actually. Okay, so let's go ahead and consider. Let's consider c1 x squared plus c2 x squared minus 1 plus c3 times 5 equals 0. And we want to see, can we find C1, C2, and C3 solving this? Not all 0 solving this. Because I mean, clearly if we put C1 equals C2 equals C3 equals 0, we can solve this. Okay, so let's go ahead and see. Well, this is actually very similar to what you do during partial fractions, right? So the constant terms. Negative C2 plus 5c3 equals 0. There's no x terms, and there is an x squared term. Okay. C1 plus C2 equals 0. Okay. Well, we could solve that with C3, let's say, equaling 1. If C3 equals 1, C2 equals 5, and C1 equals negative 5. So we can solve this. We can solve this with non-zero coefficients. So these are actually linearly dependent. Nope, I had it right. Okay, let's take a look at another. Are the functions x, x squared, x cubed, x to the fourth linearly dependent or linearly independent? Okay, now, if you look back on what we did in the last slide, I sort of said, well, one of the important linearly independent sets is 1 plus x squared plus x cubed to x to the n. This is a subset of that. So one thing I didn't say that I should have said is subsets of linearly independent sets are necessarily linearly independent. So that's one thing I could say. So subset of 1x, x squared, x cubed, x to the fourth. This is linearly independent. So x squared, x cubed, x to the fourth is also linearly independent. So I'm using a property of linearly independence that I'm introducing now. That's not necessarily true for linearly dependent sets. Subsets of linearly dependent sets could be linearly independent. Okay, now, wake up. Okay, if you didn't like that explanation, I can understand that. So let's actually do it directly. So let's consider C1 x plus C2 x squared plus C3 x cubed plus c to the fourth x to the fourth equaling 0. Now, this is a fourth degree polynomial, right? Fourth degree polynomial equation set equal to 0. And if you remember from college algebra, that means that this has at most 4 roots. Okay, so that means we cannot set this identically equal to 0. It can only be 0 at 4 places. Okay, so that means we can't find these C1, C2, C1, C2 to set that equal to 0. Okay, another way to think about it is, let's say that we just had C0 plus C1x. Okay, if you just had that, the only way that that's going to equal 0 is if x equals negative C0 over C1, right? Okay, that's the only place with C0 and C1 not equal to 0. That's the only place this is going to happen, okay? Otherwise, you're not going to be able to solve that identically equal to 0. Okay, that's another sort of example, or just another idea sort of to consider about these. Okay, all right, we're going to come back with the last sort of idea in this sort of family of ideas that we're looking at today, at least the last idea for today. And that's the Wronskian and how it relates to linear independence.